Simple harmonic oscillator is the typical pattern of the natural phenomena. So far, you stay on the classical dynamics based on the Newtonian system, and when you analyze the simple motions with the single object in free body diagram, or if you deal with when you actually handle some sort of object with a volume, um, we assume that there's one single force applied to the object, and instantaneous force produce that acceleration. But in many cases, natural force consists of restoring force, which means the force bring that object back to the equilibrium state, which means the object like to just come back to their original position with the restoring force. So there are a lot of typical examples we already studied in the past, like spring or pendulum, or maybe like waving motion in the ocean, or the mechanical object itself also have a restoring force on their structure too. So one of typical example, most common example of simple harmonic oscillation or oscillator is spring. Spring has obviously restoring force. If you just stretch the spring, then they always try to just, comes back to the original size, right? So let me create some picture. So now that's nature. Oh, hold on. Okay. That's nature of the spring. Well, if you have a spring, if you don't touch it, then there's no physical deformation. But once you push or just stretch that string in the one direction, then this string, spring always want shrink down to the original size. So that is called a stiffness. That stiffness is, driving force of restoring force, because if you attach the objects in the spring, if you put the force in this direction, there's opposing force from spring to bring the object M back to the original position. So the stiffness of string is parameterized of the spring constant K. So with that idea, now if you have the external force applied to the positive direction, let me just draw the picture. And step one, number one, then we have object attached to the spring with the spring constant K, and now T equals 0, then their displacement X equals 0. But once you put the force on that system, then you have change of displacement of this object. At the same time, you change physical size or physical length of this string too. So now, if you change that physical size, physical length of the string to X equals A, you possibly produce some energy from external force. Also, that create the potential of the spring, which bring that box back to the the object M back to the original position X equals 0. That is called the restoring force, which means that the force itself try to make the state of the object back to the original starting point, actual original position or original state. So once this object, if you just let go of this box, then this object M just moving back to the original position. And because of nature of restoring force or spring, this object M passing through that this original position, and they're just now spring itself actually just um, shrink down. And there's another, um, you know, displacement in the negative direction. Oh, hold on. Possibly just created into that this object M minus A. So if you don't have now after that, this box also like this spring starts pushing this object back to the original position. So if there's no friction on the floor, this box supposed to move back and forth indefinitely, right? This is like it has come and go with the amplitude A, and that the the source of this perturbation or oscillating motion is basically the strength of this spring. So now let's assume you have spring attached to the ceiling or roof of the room. Then you have object M attached in the air, and now you have some sort of like pen or pencil put on this box. I mean, this object M. Now you have like paper uh, sitting on top of this pen or pencil. Now you start bring this box downward, then this box will start moving up and down because of this spring. So if you trace down the mark out of this pencil, and you will see there's some sort of pattern because we'll down first and then we'll go up, and that will produce this kind of sinusoidal pattern of this pencil mark on this paper in time t. So if you put the mark on this sinusoidal pattern, and when this pencil actually come back to comes back to the starting point, then you can put that each node of this sinusoidal graph is t or 2t and 3t, 4t. So that is called a period. So basically, the source of this dynamics is obviously is gravity. Fg equals mg. That has the some sort of equilibrium relationship with the restoring force of spring force. So here, based on the Newtonian system, this F of this object exerted on this object is mass times an acceleration, right? That is minus kx, as you know, this is Hooke's law. And if you just actually analyze this one in time, obviously A itself is the function of the time, which is d2x over dt squared, right? As you know, that's the second order derivative of the displacement of the box. You plug that into this formula, then F equals MA, which is M d 2x over dt squared equals minus kx. That is complete form of a second order differential equation. So now you can see the left hand side of this formula is function of x of displacement. Right hand side also expressed with the function of x. So if you move this one to the left hand side, then you supposed to have complete the second order differential equation, which is m d 2x over d t squared plus kx. Now if you divide by the m mass, then this equation should be expressed with this formula, the d 2x over dt squared plus k over m x equals 0. So that's a typical form of second order differential equation, and it is pretty well known. The solution of this second order equation is function of sinusoidal, sine or cosine function. So usually this solution of this second order differential equation is in the form of sine cosine function. So you can actually assume that solution itself is x equal xm times cosine omega t plus pi. So here the xm itself is maximum amplitude of displacement of the object, and omega is angular frequency, which indicating that how fast this object actually oscillating or moving up and down, up and down. And this pi is initial, relate to the initial position or initial amplitude. Okay, so if you, let me just change the color. So this xm itself is pretty much same as the maximum amplitude A. That's same as A. So when you push or pull that object downwards or original direction or vertical direction, when this object M moving down or moving up and this starts toward that maximum point, and it will stop some point. So that xm itself indicating that how far this object actually can go until the object stops moving. And this cosine function, the omega, as I said, indicating that how fast this object's moving back and forth, up and down, in given time, especially 1 second. So the omega itself expressed with 2 pi f. Here's f is the frequency, and the omega is obviously the 2 pi times frequency f. Then this pi, basically naturally we assume that the boxes start from 0 position, x equals 0. But you can maybe just drag this box at some distance from the equilibrium position, x equals 0. So in that case, this pi indicating that the very first point of displacement x. Okay, so this is solution for this second order differential equation of this type of system, which consists of the spring and the object M under the influence of the gravity. So this, whatever you see, if you see that this kind of solution, which is function of the cosine or sine function, any type of solution is expressed with this combination or combination of a sine or cosine function, it is normally called a simple harmonic oscillator. Okay, so in that case, we don't take into account friction. So there's no frictional term in this solution, but um, this is standard form of any type of system which has periodic, pervade periodic actually just vibration mixed into the system. So if you touch any system and they start moving back and forth, up and down with the regular pattern, that is called a simple harmonic oscillator. We have much more complex system in later on, but that is a standard form of simple harmonic oscillation. Anything comes with the sine and cosine function as a solution, that uh, should be called a simple harmonic oscillator. And now, the first solution out of the second order differential equation is the displacement, xm times cosine omega t plus phi. Now, from that, we can also find the velocity and acceleration in sine or cosine function form. So the velocity itself of that object of simple harmonic oscillator is dx over dt. So if you plug this displacement into this formula, then that should be d over dx dt times x m cosine omega t plus phi, and that is the minus omega x m cosine, I'm sorry, the sine, this should be the sine, right? The first derivative of cosine function is sine omega t plus pi. And acceleration is d 2x over d t squared. So you plug that x into this formula, then that should be d over d2 over dt squared times x m cosine omega t plus phi. So if you just do that, and actually you need one more differentiation of the velocity v. So that would be d over dt minus omega x m sine omega t plus pi. So that should be omega squared xm cosine omega t plus pi. So if you plug this acceleration, expression of the acceleration and the displacement into original formula, which is d square x plus dt square plus k over m equals 0. So that is original second order differential equation. So if you plug this displacement expression into this formula, I'm sorry, that should be the x2. So if you plug this one into this x and plug this acceleration term into this formula, then that should be minus omega squared xm cosine omega t plus phi plus k over m xm cosine omega t plus pi equals 0. Okay, from that, if you just take the cosine function out of the first term and second term and xm2, then that could be simplified into this expression, minus omega squared plus k over m times xm cosine omega t plus pi equals 0. In order to have this equation, uh, you know, valid, then inside this bracket must be equal 0 too. Unless this one is equal to 0. Then this one, from that relationship, then minus omega squared plus k over m equals 0. From that, omega can be expressed with the two system variables, k and m, which is function of these two variables. So from this, you can find out the simple harmonic oscillator frequency, angular frequency or frequency can be determined by spring constant k and the mass of the object m. So I can just maybe give you, I should maybe ask you the question, what happened, what is the way to increase the frequency? What is the way to increase the frequency under this relationship?
Decrease the period.
So now you have like this spring, right, attached to the object, right? There's only two variable. One is mass of the object. The other one is the spring constant k. What is the way to increase? What is the way to actually make this system or object moving up and down faster? It is symbolized by this omega.
Make the mass greater.
Mass greater?
Yeah.
Why?
In order to increase omega.
If your m is increased, then omega goes down.
Oh.
Right?
Yeah.
So it's kind of quite opposite, right? You need to make this m actually lighter. Then this omega goes up. Any other way? Rather than just to put the lighter object to the spring, what other way to increase the omega or f? Is that just putting the lighter mass to the spring?
Find a spring with a higher.
Yes, another way is just to make a string steeper, so that make k values increase. So k is higher. So here k is higher, or m is lower. Then make omega. The f goes up, and omega goes up, right? Or vice versa. So if you just make a spring is steeper, or hang heavier, the lighter object to the system of spring and make this object move up and down faster. With fast, like a vibration or oscillation itself is just high going, that make the system moves faster. So that is the basic relationship of the system variable omega and the real variable, the real parameter k and m. Because k and m is the actual physical values of physical numbers out of real object, but omega is system variable, so that k and m can be determining that the system, how system actually responds to the external force. And from that, now we can define a few other system variables. So the f and omega is system variable of the simple harmonic oscillator. And there's another actually system variable, t, which is period. So I show you if you plot the amplitude of the object M in time, then they should have sinusoidal shape, sine or cosine function like this. Okay.
Mm.
So this is starting point 0, and that is the first node and second node, and first, then just that zero amplitude point appears periodically, right? So if you move this starting point all the way to here, so that's 0, and this point is t prime. Then this one exactly overlap with this t prime. Then that amplitude, it just goes back to the same shape, right? Like this. So if you plug this additional amount of the time duration into this cosine function of displacement, which is x equals xm cosine omega t plus pi. Now from that, just ignore the first page because that has nothing to do with this periodic pattern of the sine function, cosine function. Now, if you add additional time into this displacement, like this, x equals xm cosine omega t plus time, extended time t. So right there. So even if you add extra time to t and that doesn't change disturbance of this shape of this graph, then t itself is called a period. Because the once plugging that this time in additional time t, this start the same spot of this graph is repeated on the graph, then there's nothing changed. So under this condition, cosine omega t xm same as xm cosine omega small t plus large t. That is condition to define the period t, large t. Okay, because after you move this graph to right hand side with the delta, I mean this t, and still you maintain the shape of the amplitude without any change. So with that idea, let me just delete up some of this one. Hold on. Okay, so here from this relationship, the cos the omega t should be equal to the omega t plus omega large t, right?
Mhm.
So in order to just have this relationship with the cosine function, this omega t must be same as 2 pi. That's the nature of cosine or sine function, because cosine and sine function repeatedly appeared in their x-axis with the 2 pi period. So after 2 pi, the amplitude is back to the same value. So this omega t must be same as 2 pi. So from that, omega t is 2 pi. So this omega itself is 2 pi times f, right? 2 pi times frequency. So you plug that into this relationship, then there's 2 pi f times the period t is 2 pi. So you cancel that out from both sides. So the f times t equals 1. That indicate the frequency and the period, they're inversely relations. So you re-express this one is f is 1 over t, or t is 1 of f. Okay, you got to memorize this relationship, because once you find out the frequency out of the given condition, you should be able to drive the value of the period too. So you know that the number of period means you already know number of frequency, or vice versa. Okay, from this relationship. All right. Okay, so far, any question? So that is basic parameter that defining the nature of a simple harmonic oscillator. First, simple harmonic oscillator must be defined by sine or cosine function, and their basic parameter is given by amplitude xm, and their frequency f, or angular frequency omega, or angular velocity omega, and their period t, just repeated pattern. All right. And so now let's take a look at the, hold on. Yeah, let's take a look at the energy definition of this simple harmonic oscillator. So now we define that displacements, the velocity, and acceleration out of the simple harmonic oscillator in the sine and cosine functions. And now we can actually find out energy distribution of simple harmonic oscillator. Okay, so now I only give you expression of 3 different variables: displacement, velocity, and acceleration, right? So first of all, the velocity itself, I mean displacement itself, x is xm cosine omega t plus pi, and the v is minus omega xm sine omega t plus pi, and a acceleration is minus omega square xm cosine omega t plus pi. And from that, a equals minus omega square xt. It's pretty straightforward. So far, so good. Nothing special, nothing different. They're all same, based on the simple kinematics Newtonian system. So if you plug these 3 functions in the time plot, okay? So if you plug that into time plot, then the number 1, this one is the displacement. Let's just show you that this displacement plot, and I compare that with the velocity and acceleration. All right. So this is the time plot of 3 different variables out of a simple harmonic oscillator. This is displacement x, velocity v, and acceleration a. So let me plot it. Then you will see that it's more visualized the relationship between the 3 different variables, x, v, and acceleration a. So let me change the color. So displacement start with the maximum amplitude xn at t equals 0. So like this as cosine function, right? And the v, this one is sine function. So it should be the 90-degree shifted from this displacement. So that should be like this. So let me just set up the vertical line to compare three different graphs. So now the velocity itself comes with the minus sign. So you start with the minus value first, while the displacements move forward. So like this. That is, oh, gotta very carefully draw it. This cosine, this is velocity, and the acceleration, just like displacement, that based on the cosine function, but it comes with a minus sign. So it should have this kind of shape, same as displacement plot, but it comes with a minus sign. So when displacement is maximum positive and the acceleration is maximum, maximum negative. So when this x is maximum value at t equals 0, then it has maximum force. The object itself experiences maximum force to the center of displacement. Okay? All right, so that means, now let me draw the picture. You have the object attached to the spring, and you have like a maximum displacement. You start with a maximum displacement at t equals 0. Right there, maximum displacement xm. When you actually start of this oscillation, then the force is also maximum value toward the middle of this perturbation, this oscillation, up and down, up and down. Okay, let me repeat one more time. This is important because this three graph clearly indicating the relationship between the displacement, velocity, and the acceleration of simple harmonic oscillator. So when you start, you stretch out your box out of the spring with the maximum amplitude. So at t equals 0, right? Initial point, you let go of the box. Then you have maximum amplitude, but your velocity is 0, right? Because you just leave the box in the air, so there's no velocity, but force itself is maximum upward, which is negative direction with respect to the direction of displacement. So that this three graph clearly shows how that the dynamics change in time or in position of a simple harmonic oscillator. Okay, so if you leave the box with the maximum amplitude and leave it, just box go, and this kind of box gradually move toward the middle of center of that the perturbation oscillation, and but initial velocity is 0, but it's move it faster and faster upward and pass through the starting point. And when you pass through the starting point, the velocity is the maximum. It just passed through the x equals 0 at the maximum velocity. It just has maximum velocity, but the force is 0 at the x equals 0. And when you actually moves all the way to the maximum position, then it reach out to negative maximum amplitude, but the force also has the positive maximum. So it's downward, but the velocity is getting smaller and smaller and smaller and reach the 0 when this object reach the maximum positive displacement in their position. Okay, so this three graph shows that their relationship, but next one we can also find out how that actually create energy equation in the simple harmonic oscillator. Okay, so now what is the definition of the potential energy of the spring? Do you remember? Potential energy of a spring, of Hooke's law. Do you remember, Tatiana? There's what the expression of energy of the spring, potential energy.
One half kx squared.
Yes, that's correct. So that is 102 kx squared. That is potential energy of the spring. So now let's plug that the solution of x displacement, which is x equals xm cosine omega t plus pi. which we actually obtained from that relationship. I mean that the previous relationship of x, b, and a, and now we plug it into this formula, which is 1/2 k x m square cosine square omega t plus pi. Now, what is definition of the kinetic energy?
1/2 mv squared.
Okay, that is 1/2 of m v square, right? So now we're gonna plug this velocity out of the simple harmonic oscillator. I already show you that velocity expression is given like this: minus omega xm times sine omega t plus pi. So you plug that, v equals minus x omega x m sine omega t plus pi. You plug that, then that should be 1/2 m omega square x m square sine square omega t plus pi. Now let's add those two energies together and see what's going to happen. So now I want to plug them all together. UT potential energy with the kinetic energy. Let's take a look at how it goes. And so that's 1/2 k x m square cosine square omega t plus pi plus 1/2 omega, hold on, m omega square x m square sine square omega t plus pi. All right. So remember, what is omega? A simple harmonic oscillator. Do you remember? Omega was what?
The speed of the frequency.
The angular velocity, but that's I'm talking about the what? How was the omega defined by the system parameter k and m?
Root k over m.
Yeah, square root of k over m, right?
Mm-hmm.
So if you square it, then omega squared is what? K over m. You plug back into this formula, then this one must be what? 1/2 m times k over m times xm square sine square omega t plus pi, right? So now you just m is cancel out of the numerator and denominator. That's only leave that 1/2 k x m square sine square omega t plus pi. Now let's take a look at how that changed the formula of the energy term. So now the first term is 1/2 xm squared cosine square, and the second term is 1/2 kxm squared sine square omega t plus pi. So the first term, second term, they all have 1/2 kxm squared. So you can take them out of the bracket, and or you can plug the cosine and sine function all together in the bracket because they are common. I mean, they're only difference between the first term and the second term. So if you arrange that equation, then that should be 1/2 k x m square cosine square omega t pi plus sine omega square omega t plus pi, like this. Okay, right there. What is this? Do you remember trigonometry relationship?
Um, and
What is that? Do you
tangent of omega t plus y.
this one? The same as this cosine square A plus sine square A is what? Equals what?
Um,
Do you remember? Okay, well, that is simply just one from trigonometric identities. So basically, this inside the bracket is same as one. So that is just 1 over 2 k x m squared. So that k is constant number, xm is constant number. So that should be constant value, right?
hmm,
So this is very interesting result. You separately derive formula of potential energy out of simple harmony oscillator. And also you derive formula out of the kinetic energy out of this simple harmony oscillator. You just plug them those two energies in their simple harmony oscillation form, and the result comes with the constant value. So that actually sort of like proof of energy conservation. So you add kinetic energy and the potential energy and the kinetic energy, they always just bring up, I mean, that equals to the constant value. It doesn't matter what type of the kinetic energy or potential energy actually added into the system. Simple harmonic oscillator always have constant value of total energy. So total energy itself, 1 over 2 k x m squared, right? You see that I have shown you that how the total energy actually was derived from kinetic and potential energy, which is function of potential energy UT and the kinetic energy KT. So that doesn't matter what shape of the energy form you have on the potential energy and kinetic energy, the total energy is, as you can see, it always constant value, that indicating that conservation of energy in the system, simple harmony oscillator. If you plot this one, okay, hold on. In the graph, it's more clear, even more clear actually. So let me plot. So if you plot the this relationship, then now this is displacement x, and this y is energy. Could be E, U, K, any type of energy. Now, this when x equals 0, then potential energy is 0 too, right? And you stretch the spring, then potential energy just increase proportional to the hyperbolic shape, like this, right? This is the ux. And when you reach the maximum point, your potential energy of the system, simple harmony oscillator, is also maximum value. So that is minus xm. This one is plus xm, maximum amplitude of the object in the spring system. Are you with me? Tatiana, okay. Do you want me to repeat one more time?
um,
So I plotted this energy in this with the displacement. This plot, this graph shows energy versus the displacement. Okay, so x-axis is displacement of the object, y-axis is energy, either total energy E or potential energy U or kinetic energy K. Any type of energy is just plot in the y-axis, vertical axis. And x is just displacement of the object attached to the spring. Okay, so when you stretch the spring, you automatically increase the potential energy of the spring. And as you move toward the maximum amplitude xm, you have more and more potential energy. So when you reach the maximum displacement xm, then you must have a maximum potential energy. It doesn't make sense, right? You have like a stretch out with the maximum amplitude. The spring itself should have a maximum potential energy. But because of when you reach the maximum point, the velocity is zero, you have a minimum kinetic energy at the maximum amplitude. Okay?
Mhm.
So that's smallest the kinetic energy at the maximum displacement. But when you actually, as I already just explained to you, when object moving toward the middle of like the center of the system, the original position, then velocity goes up, 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 and then that produce the maximum kinetic energy. So it should have inverse hyperbolic function, the shape. The kinetic energy itself should have inverse hyperbolic shape like this. So that is kinetic energy. And once it's passed through the middle of the system or equilibrium position x equals 0, then velocity goes down, slowly just decelerate and slow down, slow down, and slow down. And when it actually reached the maximum negative displacement, maximum amplitude, then kinetic energy is the minimum value, kx. Okay, so basically the potential energy and the kinetic energy are the quite opposite, the shape with respect to the displacement of the object. So when the potential energy is maximum and the kinetic energy minimum, and the kinetic energy maximum, then the potential energy minimum. But when you add them together, doesn't matter. They're all constant value of total energy. It should be always constant value. So this straight line in vertical direction, horizontal direction is kinetic energy, total energy, EX. Because you see that if you plug this, let's pick up the 1 point right there. So let me change color. Let me pick up this point right there. And that is maybe somewhere in maybe 1/3 of XM. Then you have large amount of kinetic energy right there, but has minimum potential energy. So this amount of energy is just added to here, right there. So that creates 1/2 kxm square. Same thing if you choose maybe like a 2/3 of xm. Then at that point, the kinetic energy is slightly lower than the one at the xm/3, but you have more potential energy right there. So you plug this amount of potential energy on top of this kinetic energy, then the total energy is still like 1/2 kxm squared. Okay, so what I'm telling you, it doesn't matter where you're standing in horizontal axis. The summation of kinetic energy and the potential energy always should be same as 1/2 kxm squared. It doesn't change. That is indicating that energy conservation. Okay, all right. So that is basic concept of the simple harmonic oscillator of first part. Okay, so we have, let's see, two more actually additional concept of the simple harmonic oscillator, including damping and external force. Okay, so that the major concept of simple harmonic oscillator pretty straightforward. But once we actually look through that simple harmonic oscillator, then the major basic concept, then we'll just start looking at the example. So before wrapping, ending today's session, I will just give you just one more idea of how damping work for a simple harmonic oscillator. Okay, and then we just move on to the next session in next week. So the damping itself is just like a friction on the Newtonian system. So remember when you have the object on the Earth surface, and surface itself have frictional coefficient in mu k, and if you multiply the normal force to that static frictional coefficient, then that produce the frictional force, right? Remember, like this is force, and that is normal force Fn. Then that's surface, so a rough surface has the static frictional coefficient. So this frictional force always opposite direction against the like external force you apply to the system. That kind of idea is same as the damping in simple harmonic oscillator. Now, I already show you the basic system of simple harmonic oscillator. The object M attached to the spring in the air, which has the spring constant K. Now, let's assume that this object also have the bar with some sort of a cylinder, and that cylinder submerged into some sort of liquid with that liquid itself has viscosity. So when this object move up and down, this liquid with the submerged plate just kind of like a slow down of this object M. If when this object M moving down, this plate inside of the submerged in this liquid actually produce the opposite force in upward. When this object M moving upward, this liquid itself produce downward force. So you can think of this plate inside submerged into this liquid parallel as this friction on the rough surface. So just kind of like resistance, like it produces the opposite force to prevent the spring force over external force from actually moving with the right constant speed. So damping force under this condition, damping force itself could be parameterized or could be expressed with damping constant value B times velocity V. Okay, that's usually it's defined by this expression. So damping force itself is a function of damping constant B times velocity of object. So it tells you if object moving faster, then this damping force will be bigger. Okay.
Mhm.
So that you move faster than this, produce the more frictional force to the object M. So if you plug that into the Newtonian system, then that should be F S plus F damping equals MA. So here, Fs is spring force, F damping is damping force from this liquid, and Ma is the net force applied to the system. So from that, if you re-express this formula with the full differential equation format, then that should be Ma equals minus Kx minus Bv, and that A is d2x over dt squared. So that is m dt d2x over dt squared equal minus kx minus bv. If you move this term to the left hand side, then and divide by m, that should be d2x over dt squared minus, plus. Now minus sign should be a plus. If we move to the left hand side, then that should be b plus k x equals 0. So here v is actually also a function of x displacement. So that is dx over dt. So that whole equation, differential equation, is d 2x over dt squared plus b dx over dt plus kx equals 0. Okay,
Mhm.
so it's also like the solution of this type of second order differential equation is also pretty well known. So that solution itself comes with exponential function. So x is actually xm times exponential minus gamma t times cosine omega prime t plus pi. So the gamma itself is function of b over 2m. Okay, that is the damping factor too. So you see that this solution itself comes with the exponential function, exponential decaying function. So as time goes, if you plot this solution in time, then normally like this, you have amplitude but it's decaying like this. So the envelope of this displacement actually proportional to the exponentially decaying function. So that envelope itself is given by this exponential function. Okay.
Mhm.
So basically damping, it produced that the amplitude actually just fade away over time. And here's one more thing. Oh, here's omega prime is slightly different from the angular frequency of just simple harmonic oscillator. So the omega prime is actually square root of k over m minus b squared over 4m squared. Okay,
Mhm.
so you have additional term inside the square root. So that this is called this system, this kind of system, the simple harmonic oscillator with damping term is called damped harmonic oscillator.